Resolving vectors is a lot like resolving conflict. Like a lot of times I'll walk into the room and somebody come up to Newton and they'll be like, I don't like your haircut. And Newton's like, well, I don't like your attitude. And this guy's like, I don't like your face. And then suddenly fisticuffs, right? But I usually try to intervene before that happens, and I'll be like, let's try to resolve this using math. Resolving vectors is about finding components. So we want to find out what each vector is really made of. We want to get the components of the vectors that are in question. Resolving vectors is an important step of working with vectors, because if you can resolve vectors, then you can ultimately add them. So this is phase 2 in our adding general vectors lesson. And I wanted to tell you how to add vectors generally, but resolving vectors in particular today. For instance, this car is displaced at 45 degrees north of east by 10 kilometers. So make some lists. Lists are good, right? Here's a list. List 1. Probably want a coordinate system again, right? If you draw a coordinate system for this particular problem, you'd be like, well, it probably needs to have north and east, and that's going to be easy. If it were north and west, I would probably still show this. I'd show north here and east here, and I'm going to associate this with my y-axis and this guy with my x-axis. Another thing that should not be done is drawing, for instance, some people like to draw x over here and then y down. That's called a left-handed coordinate system, and that's really weird. You would only want to do that in certain circumstances. This is like looking at the world upside down. Please don't do that unless you really do know what you're doing. Okay, so I've drawn my coordinate system for this problem, and I think my next step is just to draw the vector. Let's do that right there. Draw vector. And I need my vector to be 45 degrees north of east, so I'm going to draw east first. That's the east direction, and I need to be north of it by 45 degrees. So 45 is splitting that sucker. I'm going to put it right there, and this is my vector. I could even name it, let's call it vector A. Vector A is pointing up there, and I'm going to label that as 45 degrees north of east. Notice it's not east of north, it's north of east. All right, then, after I've drawn the vector, then I need to create a triangle. And this is an art. You're going to get used to how to do this. Create a triangle. Sometimes, oh my gosh. Create a triangle like this. Sometimes you're going to get a vector that's pointing directly to the east. That doesn't need a triangle, because if this were our vector, let's call that guy vector B. Vector B x component and vector B y component would be pretty obvious. Let's say vector B is 10 centimeters. Then vector B's x component, because it's directly to the east, is 10 centimeters. And vector B's y component, well, it's nothing. That vector doesn't point up. It doesn't point down. All right. But in our case, we need to create a triangle, and the way to create that triangle is I can only draw dotted lines. I can only draw dotted lines along my axes. So here I am creating the triangle. I think I'll do that in blue. That's a fine choice for this problem. I want to show you that I'm going to draw a dotted line for this axis here, where it's already done. Sometimes you have to continue it a little bit longer. And then I get to make a dotted line for the other axis, and the other axis is up and down, right? So I need to put a dotted line starting at the tip of the vector and going there. And the nice thing about this is I've created a right triangle because my axes are always at right angles to each other. Now that I have a right triangle, I can do all kinds of crazy trigonometry, and I know certain relationships between sine and cosine and angles and hypotenuse and such. In fact, you might be familiar with the Native American princess named Sokotoa. She wasn't actually called Sokotoa until she was exposed to the wonders of mathematics. And it was then that she took this name. It doesn't sound like an actual Native American name. It sounds like a joke, right? But she claimed the name for herself to forever enshrine these 3 equations. She said sine equals opposite over hypotenuse, and she said cosine is equal to, adjacent over hypotenuse, and she said the tangent is equal to adjacent, so it's opposite over adjacent, right? Okay, but all of these are wrong because I've forgotten something. These are functions here. Sine, cosine, and tangent are functions. And so I need to say sine of theta, cosine theta, tangent theta. Otherwise, I'd be like saying that a function is equal to some ratio, which is like saying that Well, it's like saying that the square function is equal to 7. That doesn't make any sense. That doesn't mean anything. So I have to operate the function on a number, like the screwed up, okay, sorry, 2 square is equal to 4. It's not the square function that's equal to 4, it's 2 when it is square that's equal to 4. All right. So I've got these 3 equations, and they're going to help me find out these sides right here. It won't always be the case that I'll have it drawn in this orientation, so I'm not going to be able to say x equals or y equals, but I'm going to do this specifically for each problem. I need to find this side right here, and in this case, the side is adjacent to this angle right here, and in this case, the side is opposite to that same angle there, that theta that was given. That's 45 in this case right here. So I'm supposed to, what? Solve this equation? It's just a regular equation. You might think of it as somewhat sacred because it's got that form and it's in SOHCAHTOA and awesome, etc. But you can do algebra on this. You could solve this equation for the opposite side's length. This variable right here is just a variable, and then we're just trying to find it right here. So when I do it, I'll multiply both sides by the hypotenuse. And it will say opposite equals the hypotenuse's length times the sine of theta. What if I take this equation right here and I solve it for the adjacent side's length right there? I could take hypotenuse, multiply hypotenuse on both sides, and I get adjacent equals the length of the hypotenuse times the cosine of theta. All right, good. So then I want to just plug that into my calculator, and this is really fun. Watch this. Calculator. On. Hypotenuse's length. Check it. 10.0 kilometers. 10 times the sine of, well, I'm going to get this side first then, sine of 45. Enter. And now I'm in a little bit of a hurry, so I'm going to click second entry and get that back up there, and I'm just going to change the sine to a cosine, and boom, I've got them all. Oh, my calculator made a mistake. Something's wrong. It's not recognizing that I changed it. So I've got like, what, 3 sig figs? 7.07 kilometers, and this is supposed to also be 7.07 kilometers. Oh, it's because it's a 45, 45, 90 triangle. Okay. So, here's vector. We called it vector A, and when I'm finally finished, I can write down AX equals and AY equals. AX equals, that's this X component right here, 7.07 kilometers. And I guess it's east, right? Yeah, good. And AY equals 7.07 kilometers. Which way? North. All right, good. All right, good. Let's go on to the next problem. We're going to do this next one a little bit faster because we're getting pretty good at this. A duck accelerates at 2.0 meters per second square at a 35-degree angle from the ground. That's interesting. I'm probably, in order to draw my coordinate system, I'm probably going to draw up and over. This is my plan. I'm drawing up and over because over is like the ground. And they're not telling me whether the duck accelerates up or down, so I'm going to choose up because I'm an optimist, I guess. I'm going to emphasize that it's 35 degrees and not 45 and not 60 by making the angle, I'm measuring from the ground, so I draw a horizontal right there. So I'm going to make the angle look kind of narrow right here. And I'm going to call this 35 degrees for my calculations. I'm going to call this guy vector, let's call it vector C. Vector C is right here, and I'm going to resolve vector C. I've drawn the vector, I've got a coordinate system. I'm going to declare this to be Y and this to be X, and I'm going to switch colors now to draw the triangle. The triangle has to be continuing the dotted line that represents X until I can go in the dotted line that represents Y, which makes these guys always a right angle. The angle between X and Y is happily right. All right. And then we're supposed to find these sides. So I want to tell you a little bit of a shortcut right now. I'm thinking that it's probably going to be 2 times sine of 35 and 2 times cosine of 35. So I'll just do both those. 2 sine 35, enter, and get back again. 2 cosine 35, enter. Now I've got 2 numbers. I've got 1.1 and 1.6, 2 sig figs here. And I know based on my picture that one side is longer, so I'm just going to put them in the right place. 1.6 meters per second square, 1.1 meters per second square, and I'm done. You can check if you like that the sine is using the opposite over the adjacent, and that's why it's this side right here. And the cosine likewise is using the opposite over hypotenuse and adjacent over hypotenuse. Right. You can check all that, but this will save you a ton of time. Emphasize whether the angle is less or more than 35, and put the long side, the one that is the longer of the two answers, at that location right there, and you'll be good. So finally, to summarize, Cx equals, I would say the x component is 1.6 meters per second squared over, because I've defined to the right as over, and Cy equals 1.1 meters per second square up. Cool. Then let's go on to the third problem. The third problem has a submarine that's diving 110 meters at 10 degrees below horizontal. So I'm probably going to declare things like up and horizontal to be my axes. Horizontal. There it is. Horizontal. All right. I'm going to draw a horizontal because I need to be 10 degrees below it. And I'm going to draw that. 10 degrees below horizontal. This is my vector D, and the vector D for the submarine's dive is 10 degrees below the horizontal. And now it's time for me to make a triangle out of it. Gray. Dot, 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 dot. See that right angle right there? It's the same as that right angle right there because these are x and y axes. These components, though, which way do these components go? Do they go up or down or left or right? Well, think about this vector D. Vector D goes down and to the right, so the components need to go down, that's this component right here, and to the right, that's this component right here, because the components add up to the vector D. What I mean is, if I take D sub x as a vector, and I add it to D sub y as a vector, I will get the vector D. This is the nature of components. That's what they do. They give you the vector itself, and here's dx, and here's dy. Now, I need to find those numbers, so I'm going to do 110 times the sine of 10 degrees and 110 times the cosine of 10 degrees. And so I get 108. Wow, that's a big one right there. 108.3. That's the side right there. Oh, I only have 3 sig figs, so I'm probably going to write 108. Over here, I get 19.1 meters. Now, I need to write this more clearly down here. dx equals, dy equals, and we come upon our first particular problem. Here's a little problem. If I write down 108 meters and 19.1 meters, then I will have made a mistake. And that's because I defined up as y and horizontal as x. Can you find my mistake? Did you find it yet? Do you like intermission? I don't know. I had a pretty good time with it. Here, oh gosh, let's not use that color. Here, the mistake is this component points down, so it's negative, and I have to add that in by hand. Because I use this angle as 10 degrees, I'm not using like the angle this direction. I'm not going to do anything complicated like that. I'm just going to keep these as lengths of the sides, but then when I go down to here, I notice that this is a negative number because it's pointing downward. See? Cool. If you make that mistake, then everything's going to be thrown off in the future. So please be careful. Do not make that mistake. Here's a pregnant woman. She walks 25 degrees south of east for 3.10 kilometers. I define north as y, and I define east as x. And I draw the vector of the woman, let's see, south of east. So I got to start out by drawing east. And then she's supposed to be just a little bit south of east. Wow, this is almost exactly the same problem. Let's make her go south of west. That'll be more fun. South of west. All right, so she goes like that, and this is a small angle. It's only 25 degrees, and this vector here, vector E, is how long? 3.10 kilometers. I need to make a triangle. Triangle like this, triangle like dot 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 dot, right angle right here. All right, good. And then I'm supposed to find these components. This is E sub x, this is E sub y. Notice E sub x is going to be a negative number. E sub y is going to be a negative number. And let's find both of them. Boom, boom, boom. Ready? I take 3.1 and I multiply it by the sine of 25 and I multiply it by, I got the sine of 25 twice, cosine of 25. So I'm getting things like 1.31. Which one is that? The short one or the long one? Oh, this is the short one over here because that's an angle that's less than 45 degrees. This is going to be no, that's the short one. 1.3, how many sig figs? We have 3 sig figs, 1.31 kilometers, and 2.81 kilometers. All right, good. So we found the components and we're done. I'm gonna get out of your hair, off your computer. Goodbye. Sorry, one final thought. If you have a ramp and you have a box on the ramp, you might be inclined to draw a vector like this that represents something like, I don't know, okay, so then you might also be inclined to draw a vector like this, but if I establish my axes like that, then this angle is used to resolve this vector that's pointing directly down. This angle right here is actually theta. And I need to draw in 2 colors for you the 2 options that you have when you resolve this vector. Do you resolve this downward vector like this, as I'm about to do in orange? Here, I'll draw them both over here. Do you draw this vector here resolved like option 1, where I draw a dotted line here, and a dotted line here? Or do you resolve this vector like 2, where I draw the vector just as it was, like over here? I just need to figure out how to draw this one over here, and I draw a dotted line this direction, and then I draw a dotted line this direction. Which of these has properly resolved the downward vector based on the way that I've taught you to resolve vectors? Resolving vectors is a lot like resolving conflict. Like, a lot of times I'll walk into the room and somebody come up to Newton and they'll be like, I don't like your haircut. And Newton's like, well, I don't like your attitude. And this guy's like, I don't like your face. And then suddenly fisticuffs, right? But I usually try to intervene before that happens, and I'll be like, let's try to resolve this using math. Resolving vectors is about finding, generally, but resolving vectors in particular today. For instance, this car is displaced at 45 degrees north of east by 10 kilometers. So make some lists. Lists are good, right? Here's a list. List 1, probably want a coordinate system again, right? If you draw a coordinate system for this particular problem, you'd be like, well, it probably needs to have north and east down. Please don't do that unless you really do know what you're doing. Okay, so I've drawn my coordinate system for this problem, and I think my next step is just to draw the vector. Let's do that right there. Draw vector. And I need my vector to be 45 degrees north of east, so I'm going to draw east first. That's the east direction, and I need to be north of it by 45 degrees. So 45, and that's going to be easy. If it were north and west, I would probably still show this. I'd show north here and east here, and I'm going to associate this with my y-axis and this guy with my x-axis. Another thing that should not be done is drawing, for instance, some people like to draw x over here and then y down. That's called a left-handed coordinate system, and that's really weird. You would only want to do that in certain circumstances. This is like looking at the world upside down. Components. So we want to find out what each vector is really made of. We want to get the components of the vectors that are in question. Resolving vectors is an important step of working with vectors, because if you can resolve vectors, then you can ultimately add them. So this is phase 2 in our adding general vectors lesson, and I wanted to tell you how to add vectors.